America mines copper. It has enormous open pits, fleets of haul trucks, mills, concentrators, and industrial sites spread across several states. In 2025, recoverable copper content from U.S. mines was estimated at 1 million metric tons. And yet, in that same year, the United States was estimated to rely on net imports for 57% of its refined copper consumption. Those two facts can sound contradictory only if mining and refining are treated as the same thing. They are not. Copper does not leave the ground ready to become a cable or manufactured component. Some mine output becomes concentrate that still requires smelting and refining. Some can become cathode through electrowinning. Scrap enters through another branch before copper reaches downstream manufacturers. That is the missing middle in the American copper story. The country has major mineral resources and a large downstream industrial market. Between them sits a smaller set of processing facilities, supported by imports and recycling. The real question is not whether America has copper. It is how rock, concentrate, scrap, and imported refined metal are converted into the copper products the rest of the economy expects to be available. The first stage is mining. Ore is removed from the ground and processed to separate valuable copper-bearing material from a much larger volume of rock. But the material leaving that stage is not always the same product. For conventional sulfide ore, concentration is followed by a series of high-temperature and refining steps. The chain described by the United States Geological Survey includes concentration, smelting, converting, fire refining or anode casting, and electrolytic refining. Each term represents a distinct industrial function. Concentration raises the share of copper in the material being handled. Smelting and converting transform that concentrated material into a form that can move toward anode production. Fire refining and anode casting prepare copper for the electrolytic stage. Electrolytic refining produces refined metal suitable for downstream users. But that is not the only route. Suitable leach solutions can move through solvent extraction and electrowinning, often shortened to SX-EW. That route can produce refined cathode without sending the material through a conventional primary smelter. This distinction matters because a simple count of smelters does not describe every route by which U.S. mine output can become refined copper. There is also a separate secondary chain. Primary copper begins with ore. Secondary copper begins with scrap. Old scrap comes from products that have completed a useful life. New scrap is generated during manufacturing. Both can return copper to the supply system, but they begin in different places and are reported separately. So there is no single stream called copper moving from a mine to a factory. There are several streams: ore, concentrate, electrowinning cathode, anodes, refined cathode, old scrap, new manufacturing scrap, rod, wire, and fabricated products. The stages are connected, but they are not interchangeable. A country can mine copper, recover manufacturing scrap, and still import refined metal when the middle of the chain is comparatively narrow. The United States Geological Survey estimated recoverable U.S. copper mine production at 1 million metric tons in 2025, down 5% from the year before. That output was highly concentrated geographically. Arizona accounted for approximately 70% of the national total. Copper was also mined in Alaska, Michigan, Missouri, Montana, Nevada, New Mexico, and Utah. The list shows both reach and concentration. Copper mining is not confined to one operation or one state, but most of the country's mine output still comes from a particular region. That matters because mining is tied to geology. A mine cannot simply be moved closer to a refinery, a port, or a wire plant because another location would be more convenient. The physical operation is also more than the pit itself. Ore has to be drilled, loaded, hauled, crushed, moved through mills or other processing systems, and separated into a stream that can continue through the chain. Control rooms coordinate machinery. Conveyors connect stages. Fleets operate across distances that can be difficult to understand from a map, but mine scale can create a misleading impression. A giant haul truck and a vast pit make extraction highly visible. The quieter question is what form the copper takes when it leaves the site, and which facilities are available to process that form next. Some mine output can follow the SX-EW route. Concentrate from conventional sulfide operations requires additional processing. Those routes can involve different facilities, different transport needs, and different points of exposure. The 1 million ton mine figure, therefore, cannot be placed directly beside refined consumption as if both numbers measured identical material at the same stage. The country may possess the ore, recover the copper content, and still need another part of the chain to deliver the refined metal used by manufacturers. That is where the story moves from geology to industrial structure. To understand the processing constraint, begin with the conventional sulfide route. After concentration, the copper-bearing material moves into smelting. Converting follows. The material then passes through fire refining or anode casting before electrolytic refining produces refined copper. This is not one machine performing one action. It is a chain of furnaces, vessels, material handling systems, controls, casting equipment, and refining cells. Material changes form as it advances. Each stage has its own equipment and operating requirements. If one stage is unavailable, another stage cannot automatically perform its job. Electrolytic refining belongs near the end of that route. Anodes and cathodes are not simply two names for the same slab of metal. The refining stage is what produces the high-purity copper that downstream plants expect. The overseas footage in this chapter shows examples of smelting, refinery equipment, cathodes, process controls, and acid plant infrastructure. It is not footage of a U.S. facility, and it cannot prove how an American plant performs. Its purpose is narrower, to make visible the kind of industrial middle that exists between a mine and a finished cathode. The second route is SX-EW. Suitable leach solutions pass through solvent extraction and electrowinning, producing refined cathode without using a conventional primary smelter. That means the number of U.S. primary smelters cannot be used to claim that every ton of American mine output must pass through only 2 plants. USGS counted 14 electrowinning refineries in 2025. It also counted 2 primary smelters and 2 primary electrolytic refineries. Those categories describe different pieces of the system. They should not be collapsed into one number or treated as facilities with identical capabilities. USGS estimated U.S. primary refinery production at 790,000 metric tons in 2025. That primary figure includes ore-derived refined output, including electrowinning material as defined by USGS. Secondary refinery production was estimated at 60,000 metric tons. This explains why the middle of the chain is difficult to summarize with one headline. Some copper can bypass conventional smelting through SX-EW. Some enters as scrap. Some moves through smelting and electrolytic refining. Imports can arrive as refined copper ready for downstream use. The same country can participate in all of those routes at once. The vulnerability is not that there is no route from American ore to refined metal. Several routes exist. The vulnerability is that their capacities, locations, inputs, maintenance schedules, and products are not interchangeable. A disruption in one category does not disappear because another category exists somewhere else, and that makes the facility counts in the next stage much more revealing. In 2025, USGS counted 26 U.S. mines processing or recovering copper. It counted 2 primary smelters, 2 secondary smelters, 2 primary electrolytic refineries, 14 electrowinning refineries, and 4 secondary refineries. These are categories, not a simple ranking of plant size. A mine, a smelter, an electrowinning refinery, and a secondary refinery do different work. Still, the count reveals a system in which some processing stages are concentrated in a small number of facilities. That concentration became visible in the 2025 production data. USGS estimated that domestic refined copper output fell 9%. The agency attributed the decline to planned maintenance at both primary smelters. Planned maintenance is not the same as a breakdown, and a 1-year decline is not proof of permanent incapacity. But the result shows how activity at a small number of facilities can appear in national output. When a stage is concentrated, scheduled work at a few sites can change the total even while mines, recyclers, and downstream manufacturers continue operating. The system was not standing still. USGS reported that production began in 2025 at a new Arizona mine, a new secondary smelter in Georgia, and a new secondary refinery in Kentucky. Those additions matter, but they should not be assigned capacities or treated as proof of self-sufficiency without a separate current source. A new mine does not perform the same function as a new refinery. A secondary smelter processes scrap rather than replacing every primary route. A project beginning production does not mean it has reached an assumed design output. The more accurate picture is a chain adjusting one stage at a time. New extraction, new secondary processing, maintenance at primary facilities, and imports of refined metal can all occur in the same year. That is why the import numbers do not cancel the mining story. They complete it. U.S. apparent consumption of primary refined copper plus copper recovered from old scrap was estimated at 2.2 million metric tons in 2025. Refined copper imports for consumption were estimated at 1.7 million metric tons. In 2024, that figure had been 903,000 metric tons. The comparison shows a large year-to-year change in the imported refined volume, but it does not mean that imports represented every form of copper used in the country. The more precise measure is net import reliance. USGS estimated that net import reliance for refined copper was 57% of apparent consumption in 2025. That sentence needs every one of its qualifiers. It is refined copper, not all copper. It is net import reliance, not the gross share of every copper-bearing material crossing the border. And it is a 2025 estimate, not a permanent ratio. The source mix was also concentrated. Across the 2021 through 2024 period, USGS attributed 68% of U.S. refined copper imports to Chile, 16% to Canada, 7% to Peru, 6% to Mexico, and 3% to other sources. Refined copper represented 88% of all unmanufactured copper imports in that import source table. The images in this chapter show two different parts of international copper logistics. Footage from Peru shows concentrate loading. Footage from Spain shows cathode unloading. They are not one documented route, and neither is a U.S. shipment. Concentrate is an earlier stage product. Cathode is refined copper. The distinction on screen is the same distinction in the statistics. Imports can bridge the gap between domestic refined output and downstream consumption because cathode can move toward rod mills, brass mills, foundries, and manufacturers. But the bridge also connects American industry to a concentrated set of external suppliers. That does not mean those suppliers are unreliable. The locked data do not make that claim. It means the structure of the chain extends beyond U.S. mines and U.S. processing plants. Domestic manufacturers depend on the combined performance of mining, refining, recycling, trade, transport, and inventory. The import bridge is therefore not evidence that American mining is irrelevant. It is evidence that the stage at which copper enters the country matters. Recycling adds another major route into the American copper system. USGS estimated that 160,000 metric tons of copper were recovered from old post-consumer scrap in 2025. Another 760,000 metric tons were recovered from new manufacturing scrap. The difference between those categories matters. Old scrap comes back after a product has been used and discarded. New scrap is generated while products are being manufactured. It can be cleaner, more predictable, and closer to an industrial recovery loop, but it is still linked to manufacturing activity. USGS estimated that copper recovered from scrap contributed about 30% of U.S. copper supply in 2025. That calculation includes both old and new scrap. 30% is large enough to make recycling a central part of the story. It is not large enough to justify the claim that secondary copper can immediately replace every primary source. Scrap has to be collected, sorted, prepared, melted, cast, refined where necessary, and returned to a form a downstream customer can use. Different scrap streams have different compositions and histories. The secondary chain has its own plants, equipment, logistics, and capacity limits. USGS estimated secondary refinery production at 60,000 metric tons in 2025, while also reporting much larger recovery from old and new scrap across the wider supply calculation. Those figures are not interchangeable because they describe different measurements within the secondary system. The U.S. recycling footage shows scrap yards, furnace operations, molten copper, pouring, handling equipment, warehouses, and plant exteriors. It makes visible a route that begins not in a mine, but in discarded products and manufacturing remnants. Recycling improves resilience because it creates a domestic source of copper-bearing material and keeps metal circulating. But it does not erase the need for mines, primary processing, refined imports, or downstream capacity. It is a parallel supply chain, not a substitute for the entire chain. Refined cathode is not the final product most Americans encounter. It is an industrial input. In 2025, USGS reported that refined copper and scrap were consumed at about 30 brass mills, 14 rod mills, and several hundred foundries and miscellaneous manufacturers. This downstream network changes the scale of the story. The middle of the chain may be concentrated in a small number of smelters and refineries, but the material leaving that middle serves a much larger field of industrial users. At a rod or wire operation, copper moves through another series of machines. It may be melted, cast into rod, drawn into smaller dimensions, insulated, tested, wound onto reels, stored, and prepared for shipment. Other facilities turn copper into brass products, castings, or specialized components. The exact route depends on the product. A heavy conductor is not made like a fine wire. A cable plant does not perform the same function as a refinery. A laboratory testing a cable is not proof of primary copper production. What the plant floor footage does show is continuity. Refined metal does not remain a cathode stacked in a warehouse. It becomes feedstock for production lines that expect consistent material, predictable dimensions, and scheduled deliveries. This is why a bottleneck in refined copper can be felt far from a mine or smelter. The downstream system is broad, specialized, and distributed. A manufacturer may not need ore or concentrate. It needs copper in the form its process was built to accept. The chain is therefore defined by handoffs. Mine output has to become the correct intermediate. Refined copper has to reach the correct mill. Rod and wire have to reach the next manufacturer. At each stage, the quantity may look like copper, but the industrial form determines what can happen next. Copper sits inside a larger infrastructure debate, but the facts have to remain separated. In July 2026, the Department of Energy released a draft National Transmission Needs Study. DOE described a pressing need for additional transmission infrastructure tied to data centers, manufacturing, large industrial loads, electrification, interconnection needs, and congestion relief. That finding establishes grid context. It does not provide a locked forecast for how many tons of copper the United States will require, and it does not prove that a copper shortage will occur. In March 2026, DOE also announced an approximately $1.9 billion spark funding opportunity for reconductoring and other advanced transmission technologies. A funding opportunity is a policy mechanism. It is not completed construction. Copper's strategic status changed as well. It was added to the final 2025 U.S. list of critical minerals published on November 7, 2025. Trade policy addressed a different section of the chain. A July 2025 proclamation initially imposed a 50% tariff on the copper content of covered semi-finished copper products and copper-intensive derivative products. But that is no longer a complete description of the active regime. A later proclamation, effective April 6, 2026, shifted covered copper articles to duties assessed on their full customs value. It placed most listed copper articles in a 50% tier and other listed copper articles in a 25% tier, with lower treatment available in specified cases. The exact duty depends on the product's tariff classification and the annex in which it appears. On June 8, 2026, another proclamation changed the threshold used to treat copper in a product as entirely American from 95 to 85% by weight. The original 2025 proclamation also directed domestic sales measures for high-quality copper scrap and U.S.-produced copper input materials. Those directions concern how material moves through the chain, but this script does not claim a particular plant response or future supply outcome. These policies do not solve the same problem. Transmission funding addresses grid infrastructure. The critical minerals list identifies strategic importance. Copper tariffs change the import treatment of listed articles. None of them by itself proves a copper shortage or creates new refining capacity. The honest connection is narrower. America is preparing for more transmission and industrial activity while changing the rules governing where copper enters and leaves its supply chain. A more resilient copper chain cannot be measured by one mine, one smelter, one recycling plant, or one tariff. Mining determines what can be recovered from American geology. Concentration and leaching determine which processing route the material can enter. Smelting, electrowinning, and electrolytic refining determine how ore-derived copper becomes cathode. Recycling creates a second source from old products and manufacturing scrap. Imports connect domestic users to refined metal produced elsewhere. Rod mills, brass mills, foundries, wire plants, and other manufacturers turn those inputs into useful products. The 2025 figures show all of those systems operating at once. They also show why the middle matters. Planned maintenance at 2 primary smelters appeared in national refined output. Refined copper net import reliance reached 57%. Scrap supplied about 30% under the USGS calculation, but not all supply. New facilities began production at different stages. The evidence does not support an absolute claim of no domestic refining capacity. It does show that mining alone does not guarantee refined supply. The machines at the center of the story do not all perform the same job. Neither do the policies. Resilience comes from understanding each stage clearly enough to strengthen the right one. America's copper challenge is not simply finding more metal. It is keeping every transformation between the mine, the refinery, the recycler, the mill, and the final manufacturer connected.